Hi, and good day to all of you again. So, we are on our Power Systems 2, Lesson 5, and under that, we have Power System Analysis on per unit systems problem solving. So, if you want to have the copy of these problems, so you can go to the description tab and then click the link. And then from the link, you will be transferred to a drive wherein you have the main problems and supplementary problems for you to solve. Okay, as usual, we will read the problem first and then solve it using this whiteboard. Okay, let us read the problem number 1. Let a 5 kVA 400 by 200 volt transformer be approximately represented by a 2 ohm reactance, which is referred to the low voltage side. Considering the rated values as your base quantities, express the transformer reactance to a per unit quantity. Okay, now this is the solution here. Now you can refer the solution here in the primary or the secondary side. But we need to jot down the voltage. Okay, so we have a 400 by 200 volt and we will stick, okay, to the 200 volt as our reference at the secondary side. So you have your primary and then your secondary side. So we will refer to the secondary side in this problem. Okay, we have the S base 5000 kVA, V base 200 volt, and the reactance actual value is 2 ohms. So going back to circuits theory and all of the formulas that we have already considered from the past, but it will become base computation for now. I base is equal to S base over V base. So by dividing 5,000 by 200, you have 25 amperes. Okay, next you have J base, as usual, like Ohm's law, V base over I base. So the answer is 200 over 25, you have 8 ohms. And thus, per unit is whatever the actual all over the base. You have the actual value of 2, and you have 8 as your base value. The answer is, okay, it must be in reactive J.25. So, Chipips kapatid, a very simple problem. Okay? But we implement the base computations using basic formulas. Okay, let us move forward to problem number 2. This is a former board exam problem. Okay. A 345 kilovolt transmission line has a series impedance of 4 plus J60 ohms and a shunt admittance of J2 times 10 to the negative 3 Siemens. Using a 100 MVA and the line voltages as base values, calculate the per unit impedance and admittance of this line. Okay, going back to the given, you have your V base 345, S base 100. The actual value is 4 plus J60 and Y actual is J2 times 10 negative 3 Siemens, not Siemens. But anyway, that's also the same. And this is also in terms of mho unit. Okay, so we already described some of the formulas here. If you want to get Z base, you have KB squared over MVA. So by having 345 squared divided by 100, we have a 1190.25 ohms. So by using again, these are the requirement of the system, just direct substitution, that ZPU is actual all over the base. Actual is 4 plus J60 and then 1190.25. The answer is 0.03 plus J 0.0504. Please take note, by the way, that these values here is in per unit, yes, per unit or dimensionless. So there's no unit at all. Okay, so this is the answer for ZPU. Now for YPU, it's the inverse of your impedance. So you have Y actual over Y base, but Y base is simply equal to 1 all over Z base. So that's why it becomes 1 over 1190.25. And then you need to divide it by J 2 times the negative 3. And hence, our final answer here is J 2.38. So, a very, very simple problem for a board exam problem. So, we will continue on problem number 3. Hi and hello to all of you. So we will continue our discussion on problem solving on power system analysis per unit systems. We are in problem number 3, so let us read the problem first. A 3-phase connected Y-connected 6.25 220 volt synchronous generator has a reactance of 8.4 ohms per phase. Using the rated kVA and voltage as the base values, we need to determine the per unit reactance. And then refer this reactance to a new base value of 230 volt 7.5 kVA base. Okay, so here is the solution, and it is a straightforward solution, guys. So first, you need to know what is the S base on the problem. So you have 6.25 MVA, 6.25 VA rather. You have also 220 volt voltage base. Please take note that we are on the 3-phase 3-wire system. So we need to check first if your apparent power is in terms of total and the voltage base is in terms of line to line. So since it is not mentioned on the problem that your S base is single phase or your V base is not line to line, so we can already assume, okay, this is both okay, that this is in total apparent power and this is in terms of line to line base. And then we have here your X actual, which is 8.4 ohms. Okay, I need to have a J there corresponding to a reactor. Now we can now substitute all of the values, okay, of your bases to get I base and Z base respectively. So here your I base is S base all over V base, all over square root of 3 V base. The square root of 3 here corresponds to a 3-phase system. So you have 6250 all over square root of 3 times 220. The answer is 16.4. Now we need to get Z base here. So Z base, V base over square root of 3 of I base. So V base is already present here as 220. Okay, your I base is 16.4 and then square root of 3. So manipulating this equation, values here, we have 7.745 ohms. Of course, we have X per unit, which is X actual over X base. However, this X base here is also the same thing as Z base, which is equal to X base equal to R base, simply because you're considering an ideal transformer. So you have 8.4 over 7.745. The answer is J 1.0845 in per unit. Okay, now you need to express this one in another form of per unit value in terms of the new bases. So this is the new value here. So go back to what we have described or discussed on basic fundamental or concept, the change of base formula or the forever formula. So the forever value here is definitely your S base, and then from there you divide by S given, then you cross multiply so that you can get V given at the squared here of the open and close parenthesis, which is V given, and then S base, V base at the denominator part, and then X new equal to X old. So that's the technique in memorizing this formula. Very, very basic formula and very, very powerful as well. Okay, if your base is 230 and you have 7.5 kVA, so in this case, just substitute in this formula here, considering the given value of 220 and 6250 respectively. So S given is 6.25K, your new value 7.5K, K will cancel out, and then your V given is 220, and your new base is 230, then it is squared. Okay, you multiply all of them by 1.0845. The answer is J 1.1907. And again, a very, very useful tool here is the change of base formula. If you see there is already a percentage reactance and you want to convert it to new base, don't hesitate to use the change of base formula. Okay, we can proceed to a power system already and apply the fundamentals of per unit systems. Okay, now let us move on to our interesting problem here. Okay, so we will apply the fundamentals now of per unit analysis in solving this single line diagram of a power system. Okay, you can see here that instead of reading the problem, I already given the single line diagram. But if you want to have the copy of the problems again, okay, it is already included this problem here. You can download the link on the subscription tab of this video. Then from there you can see a link that gives you the problems of this topic plus supplementary. So please practice those problems so that you can master what we have already done on this topic. It's a very, very interesting topic. Okay, so okay, let us have this problem here. Let us characterize or analyze this problem that we have here a power system, and it's pretty clear that there is no connection between these transformers. So we can conclude that the problem is a single phase 2-wire. So why we need to do that? Because when we go to the base computations, we need to know what formula that we will use. It is a single phase or a 3-phase. But the only difference is, as I have mentioned before, that if you have a single phase, you're considering V line to neutral and then S single phase. But if you're considering 3-phase 3-wire, you're considering line to line and total kVA. But here you have single phase 2-wire, so you expect that some of the formulas here does not have a denominator of square root of 3. Okay, so you have two transformers, and as you can see here, the transformers has its corresponding per unit. This already in per unit, these values here. In per unit, the values of your the values of your reactances in per unit. And then you have your voltage, your apparent powers, your line impedance here. So this X line, so you expect there is a J there. And then you have 0.9 plus 0.2 per unit as well for the load. And you have a 220 volt. Okay, now on the problem, we must use the basis of S base, which is 30 kVA on transformer 1. And 240 volt at the primary of transformer 1 as well. Actually, you can use any number that you want on this S base here, and you can also select what voltage here on the specified region. I forgot to mention, it's already regionalized this problem. Look, you can see the broken lines here. I already subdivided the power system into sections or regions. We have region number 1, we have region number 2, and we have region number 3. Okay, in this case. So it means that if you have this transformers here, you have 2, you expect you have 3 regions, but it depends on the power system, as long as it has the same base per region. Okay, we can select where we start on the solution. You can start at 115 at region number 3. You can start at 480 or 460 at region number 2. Or you can start at region number 1 using 220, 240. The answer is still the same. Okay, maybe on your exercises, on your supplementary problems, we have that kind of exercise. So, for this, I use 240 volt, okay, for formality. Since we usually use that on the first region, the solution. It's just the starting point of the solution. Wherever your voltage is, that will be the starting region. So since we start at region number 1, subscript 1 is region number 1, why there is no subscript at S base? Because S base is constant. Okay, now in this case, you have V base number 1 as 240. You can now get Z base here. So just recall, your Z base is V base squared all over S base, right? So it can be either line to neutral, line to line, and then this one S phase, S single phase, or S total. But since we have a single phase 2R line, so you have 240 squared all over 30K already, since you already have this given. Please take note that the S base is forever. That value will be forever from the input to the output. They are the same. Okay, doing so, you have 1.92 ohms. Also, since this is a transformer, another recall. Okay, we will have a separate topic on AC transformers. Okay, so this is just a recall from your undergrad, since you're talking about here refresher type of topics. So your A, or transformation ratio, is voltage 1 or primary over secondary. 1 is primary, 2 is secondary. It can be either be I2 all over I1 or simply N1 all over N2. But in terms of impedance, Z1 over Z2. So please take note, these are transformer fundamentals. So we have here in terms of V base over V base 1 over V base 2. Primary, secondary. Primary, secondary. Okay, get V base 2, our main goal. So you have V base 1, 240. And your A1 is in terms of voltage, right? Okay, so for that, you have 240 over 480. The answer is 480 volt. Doing again the same pacing here, that Z base is 480, or V squared all over S base. 480 squared over 30K is 7.68. So you already have these two important parameters in building your per unit equivalent circuit, which is V base and Z base. Okay, so if you're building a circuit, you see on the circuit the voltages and the impedances. The currents, I base, we will come back to that later if we needed to solve the currents on every region of the system, or in a certain region of a system. Okay, going to region number 3. On the third region, your transformation ratio A is equal to V base 2 over V base 3. We already have V base 2, so V base 3 we do not know. So rearranging the equation, V base 3, your A2 is 460 over 115. And you have 480 now. So by calculating, you have 120 volt. And then you can now get Z base 3 by having V base squared over S base. So you have 120 squared over 30K, you have 0.48 ohms. Please take note, when you're doing base computations, you only change the magnitude part, okay, of the actual value, because you just only use magnitude parts only, or magnitude parts on the polar form. Please take note of that. And if we divide the actual by the base, you're considering now your per unit value, which is one of the basics of our fundamentals that we have discussed on the last few slides. Okay, let us continue this problem on the next slide. Okay, so we will continue our discussion on problem number 4. So I retain the diagram here, so that when we convert to per unit of the sum of the per unit reactances here, we can have a reference on the formula for the computations. Okay, our second step is you need to convert the to per unit the system reactances that you see on the single line diagram. Our first step is base computations, and we already have these bases here and the computations on every region. So you have only 2 percentage reactances on the system. First, a transmission line 1, transformer 1, and second is on transformer 2. So if you see percentage reactances in per unit, or in percent, you use the forever formula. Okay, that we have already described on the past few slides. So it is forever because of the S base. It will not change all throughout the computation. So you have X new per unit is equal to X old V given over V base. You squared that, and then S base all over S given. So please take note, you will use the forever formula if and only if you have per unit values or percent. You want to convert these values here to its new base or corresponding new base. Now we can have the transformer one here at first, and then we need to refer it to the primary side. So I have here primary, secondary here. So you can determine primary if that is on the source side, secondary up to the load side. So it's very clear that you have the primary, secondary. And you have 240 and 480 volts here. And we will make use of the primary side voltage. So the primary side voltage here is definitely this 240 here. Okay? So if we do that, you have 240 for the given. Then 240. So this is at region number 1. If you can still recall, V base number 1 is 240 as well, because the transformer given is on region number 1. And then the base value is 30K, that's the forever. And then 30K for the given. As you can see here, you can have J.1 as well, simply because V given and V base and S base and S given is the same. Now, we can do that if also the same thing if we use the secondary as your reference. So if you do so, the only changes in the calculation is, okay, I can erase this part, is the squared, and then you have 30K. The only parameter that is changed here is the given at the secondary side, which is 480. So we have here V given from the formula is 480. Okay, this is in the second region. So based from our computation at V base 2, we have 480 as well. And you have 30K, the forever, and then you divide it by 30K as well. So the answer here is definitely the same. So the moral lesson of the story is, in a transformer, considering an ideal transformer, the per unit reactances referring to primary and secondary is also the same. So that's in principle. It's also the same here when we compute it using this single line diagram. You can also do that on your transformer too, using the forever formula, and we use the primary. So we have V given here is 460. Okay, you have 480 for the voltage at the V base number 2, and then you have 30K over 20K. Now please take note, the 480 here is V base 2. Okay, if you do so, you have 0.1378. Now, if we have the same thing on secondary, we use it as our reference here, it will also yield with the same answer. So you have 0.1. Then if you use the secondary side as 115, and then if you can still recall, region number 3, V base rather, is 120. You squared, and then you have 30K all over 20K. So again, it will yield with the same answer as well. So again, in conclusion, whatever your reference, it can be left or right, primary, secondary, the answer is still the same in terms of ideal transformer in per unit analysis. Okay, so we already have these values here, which we will make use on the next slide for the PUEC. Our next calculation here, step, is the conversion to per unit of active and passive elements. So when you say active, these are your generators, while when you say passive, these are your loads and transmission lines. So if you have values of volts, amperes, and ohms, and you want to convert it to per unit, our next formula is the per unit is equal to actual all over the base. If you have these values that you see on your single line diagram, such as your generator 1, your transmission line, and this load, there are this in ohms, obviously, are in ohms and volts respectively. And if you divide it by the base computation from the previous slide, you can obtain a per unit value. So we will continue the conclusion of this problem on the next slide. Now, we can now proceed to the conclusion of this problem here. So, from the last slide, we convert all of the per unit impedances or reactances to its corresponding base. And then, now we will convert all of the active and passive elements to per unit using the basic formula of actual value. You divide it by the base value. Please take note, you go back to the computation of the base computations on the previous slide so that we can already compute for the per unit values of these components. So first we have the active element. We have only one generator, so you have Vg per unit 1. Actual is what, 220. You divide it by 240. It's pretty basic that the generator is located at region 1, so we have V base 1 as 240. By dividing 220 by 240, 0.9166 or 0. Now another component that you need to convert is this passive elements X line and load. Okay, we have here XL per unit. Actual is 2. Please take note, there's a J there. And you divide it by 7.68 because that is J base 2. Please take note that in terms of the bases, since ideal, these are the same, R, J, and X. So the answer is J.2604. And last but not the least, since we have your load at region number 3, the 0.48 here is the J base at region number 3. 0.9 plus J.2, you divide it by 0.48. The result is 1.875 plus J, 0.4166. Now, we can now proceed to the development of the per unit equivalent circuit or PUEC, and we have this AC circuit. Now, you have your AC circuit here, which is in terms of in a per phase fashion. Since single phase, no harm done. You do not need to divide it by square root of 3. So this is your generator voltage, this is your X line, this is your load, and then these are the transformers T1 and T2 respectively, which is we convert the reactive elements to its new base. And these are your regions. As you can see, the transformers here is replaced by these reactors here. So since you already have the models of those components and then you integrate it, you already have your AC circuit, and the next step is your basic AC circuit analysis that you have done from the past lessons. And hence, to get your IPU here is already constant all throughout since they are connected in series. You just use Ohm's law. Total voltage you divide by the total impedance in series. So you need to add all of the impedances or reactances here, and then you divide it by the voltage 0.9166. It will have a value of 0.93 bar negative 26 degree. So this is an exercise for you. This is just an option. If you use another base here, for example, you use Kobe Bryant 24 kVA, and you compute again, the procedure that we use until you go to your PUEC and then you obtain your IPU. To see if your answers are correct, you must have the same angle displacement on the answer. Simply because on per unit analysis, we only change the magnitude. We scale the magnitude to per unit. But the bar angles, as you can see on the process, did not change at all. So that is the one thing that you can check if your computations is correct. Just change your S basis by your favorite number. And that's why it is called forever. And last but not the least, to get the actual value, which is from here, actual is per unit multiplied by base, then That is I base times IPU. However, how can you get I base? It must be on the third region simply because your load here is on the third region. And based on the computations, on the base computations, we have your V base 3, you divide it by, say, base 3. 120 over 0.48 times the magnitude only of your per unit current, 0.4393. We have obtained the value of 109.825. Hopefully, this helps you technically on solving per unit problems, especially considering a power system. That's the application of per unit. So what will you will expect on the next lesson? Okay, we will compute faults, definitely. We will start at symmetrical fault and then go into unbalanced fault. So thank you very much for your support and to those who already subscribe on my channel. Maraming salamat po.